So the homework problem we're looking at for Chapter 2 is number 27. And it asks us to calculate the reversible expansion of a perfect gas that is not isothermal. And to do this, we're given an expression for the temperature, which is varying in this case. So our first step is to look at what is our generic expression for work. And in this case, because we are working with a perfect gas, we can substitute our nRT over V for that P. And because our N and R are constant, we can pull them out. So this is the basic structure we're working with. However, again, we are given this expression for our varying temperature. And to make things a little easier, we're going to multiply it all out. So we get 3 separate values. We can input each of those into our T value seen above in the work expression to get this full integral. However, the problem is this looks a little complicated, so the best thing to do in this case is to break it into parts. Because we have 3 expressions that are all over V, we can actually break this into 3 separate integrals, which we'll do down below. So we've just taken each of those values of this temperature and made their own integral over V. The next thing we can do is simplify each of these integrals. So as you can see for the first one, we can pull out the initial temperature as a constant, and we're left with 1 over V. For the second one, our 2 V's cancel each other in the integral, and we're left with just C. And for the third, we can pull out our C, which is a positive constant given in this problem, and our V initial, which is also a constant. So as you can see here again, we have 3 parts of this expression, all multiplied by this constant minus nr. So we'll evaluate each of these 3 parts individually, starting with part 1. With part 1, all we have to do is know that we recognize this special case 1 over V and multiply it by our initial temperature constant. So we'll evaluate the natural log of V from V final to V initial, and because we have those special natural log subtraction rules, we end up with our first part being temperature initial times the natural log of V final divided by V initial. For part 2, it's a little tricky because we just start with C and no V because our V's canceled. How I like to look at that is just a V to the 0 power, because that equals 1. And that helps us figure out what kind of value we're going to integrate between. And if you remember, you just add 1 to your exponent and divide then by that number, which is in this case 1. So we can pull out our C as a constant, and we're just evaluating V itself from V final to V initial. So we're left with C times V final minus V initial. Part 3 is almost exactly like part 1, where we have, in this case, 2 constants pulled out, our same special case 1 over V. So we're looking at the natural log of V between V final and V initial. And again, with those special subtraction rules for natural logs, we're left with C times V initial times the natural log of V final over V initial. Then we can plug these 3 parts in to get our full new expression for work when our temperature is changing. The last thing we can do in this case is, because we see our terms are very similar for parts 1 and 3, we can potentially group them and multiply out our minus nr to make a little shorter expression. The reason we might do this is because part B of this question asks us to compare this work expression to our isothermal expansion, which is at constant temperature, given by this equation. As you can see here, we could potentially compare the first part of our new equation to the original part of an isothermal expansion. But what you'll find is that altogether we can't say if work is increasing or decreasing, because it really depends on the values of our initial temperature, our initial volume, final volume, and our constant C. And that's it for this problem.